Hello, class. So in the last video, we defined what an interval of definition is. It's something that we've been using already, right? I've been talking about it, maybe not calling it the interval of definition, but talking about in what interval is a solution to the differential equation actually defined. Talked about it a lot in section 2.4 with the existence and uniqueness theorems, and I basically talked about it now, right? And then as I mentioned, the more we talk about, the more the class goes on, the more I want to include the interval of definition in our work because it's important. Like I mentioned, it doesn't make sense to look for solutions that don't exist or work with solutions that are defined on intervals which don't make sense for the context of our problems. Right? Because we saw here, I just basically worked a couple of examples where we see things that might affect the interval of definition. Again, interval of definition is just the x values or the largest interval in terms of x values for which a solution to a differential equation is a solution. Right? So we saw some things. We saw the original differential equation. Actually, let me look at this one. The setup of the differential equation itself can give you constraints. Here, for example, x has to be greater than or equal to 0. And it also gives us a restraint on the actual function, right? Y has to be greater than or equal to 0. Okay. So those were some things that could affect our interval of definition. Once we have solutions, the actual domains of the solutions could affect the interval of definition or not. We saw an example here where it didn't, and an example where it did affect the interval of definition. So again, keep track of this. It's very important, and I want to include it more as we go on, right? So as I mentioned in the next homework, I'll probably, every time I ask you to solve a differential equation, I might ask you to give the interval of definition for some specific cases of functions. Now, as I promised, I didn't get to it in the previous video, but we talked about how the superposition principle, how given that you have any number of solutions for a differential equation on the interval of definition for these solutions, then a linear combination of those solutions is also a solution. Right, so here we're given that y1 equals x squared, y2 equals x squared ln of x are both solutions to the homogeneous differential equation given here. So it follows that any linear combination of it is also a solution. However, we need to see on what interval of definition is this true. Right? So any solution of this form is also going to be a solution to the differential equation on the interval on which both of these are solutions. Right? So let's find what that interval of definition is for both y1 and y2. So for y1, well, let's first look at the differential equation itself. There's no restrictions on what x and y can be. Right? There's no square roots or dividing by x or dividing by y. So we don't have to worry about anything there. Let's do worry about what the functions actually are. For y1, our function is x squared. Obviously, we can plug in any value here. So the interval of definition for this one is just all real numbers. For y2, however, we have the function x squared ln of x. We know that for ln of x, the domain is only x values greater than 0. So this restricts our interval of definition. So let me call this one I1. So for this one, the interval of definition is going to be 0 to infinity. Now, any linear combination of these two functions is going to be a solution on an interval of definition that works for both of them. So what's the largest interval of definition that works for both y1 and y2? Well, we can take the smallest of these, right? Because 0 infinity is contained in negative infinity to 0, right? So if we have a solution that works on 0 to infinity, it's also going to work in negative infinity to 0. So we take the interval of definition for these two functions to be 0 to infinity. So that means that any linear combination, by the previous theorem, any linear combination of these functions, so it doesn't matter what C2 and C1 are, they can be anything, is also going to be a solution on this interval of definition. Okay. And that's basically how you apply that theorem. Given any number of solutions, find the interval of definition on which all of them are solutions, and then any linear combination of them is going to be a solution on that interval of definition. Now, that's the superposition principle. Now we're going to start talking about something that's going to get a little bit more theoretical, right? So it's going to start a little bit theoretical. Thankfully, there's an algorithmic way to work with this definition. Okay, so bear with me with the theoretical part. It is important, especially when you start working in more advanced mathematics. Right? But for now, but as I said later, we're going to see a way of working with this definition that for which there is an explicit algorithm. Right? Okay. So definition two, a set of functions, f1, f2, all the way to f of n, functions of x. So a set of functions is said to be linearly dependent on an interval I if there exist constants c1, c2, up to cn, not all zero, right, that's the key part, not all zero, such that this equation, so take the linear combination of these functions, set it equal to zero. Um, if this is true, right, so if this equation is true, for all x on the interval I, where not all of the constants are zero, then we say that the functions are linearly dependent. Right, so it's a little bit of a complicated definition, but basically, given a set of functions, you want to test if they're linearly dependent, look at this equation here. If there are constants for which not all zero, for which this equation is true, for all x on an interval I, then that means the functions are linearly dependent on the interval I. So notice here that this means that you could have functions that are linearly dependent on an interval, but not linearly dependent on another interval. Okay? So I still know that this is like a crazy definition to work with. Like it's kind of hard to see where it's coming from and also how to work with it. So I'm going to do an example afterwards. First, let's give a name to what happens if the functions are not linearly dependent. So if a set of functions is not linearly dependent on an interval, then we say they are linearly independent. So you can approach this two different ways in case whether you want to see if a set of functions are linearly independent, and that's what we're mostly going to be interested in, linearly independent functions. You can either check that they're linearly dependent, that they're not linearly dependent on an interval using this definition, or you can use this alternate definition. Right? A set of functions are linearly independent on an interval if it means that the equation, this equation here, the same equation as before, has solutions if and only if all the constants are zero. So I forgot to write that equals zero there. So again, a little bit messy and a little bit hard to understand what is going on. So let me just recapitulate. To test whether a set of functions are linearly dependent on an interval, write down this equation. I'm gonna underline it again. Write down this equation and check whether it's possible for that equation to be true for all x on whatever interval you're working on when not all the coefficients c sub I are zero. So at least one of them has to be non-zero. On the other hand, how do you check if a set of functions is linearly independent? Write down the same equation, and at this time check that the only way this equation is true for all x on your interval is if all of the coefficients are zero. Let's see examples of this. So the functions f1 equals cosine squared, f2 equals sine squared, f3 equals secant squared, and f4 equals tangent squared are linearly dependent on the interval negative pi over 2 to pi over 2. Why? Well, if I'm saying that this is true, then there have to be constants, not all zero, at least one of them non-zero, for which this equation is true for all x on the interval negative pi over 2 to pi over 2. Right? So anytime someone says that these set of functions are linearly dependent, then such coefficients must exist. And they exist. I'm telling you what they are. And we can verify this. Let's plug in these coefficients into this equation above. Let's call this equation star. So if we plug in those coefficients into star, what do we get? Well, C1 is 1, so we get cosine squared, plus C2 is 1, so we get sine squared, plus C3 equals negative 1, so we actually get negative secant squared. And then C4 is 1 again, so we get plus tangent squared x. Again, I just plug those coefficients into this equation. So it must be that this equation is true for all x in this interval. So is it true that for all x in negative pi over 2 to pi over 2, this equation is true? Well, we can check. And in fact, we can check that this is the case using some linear algebra, some trigonometry. We know from trigonometry that cosine squared plus sine squared equals 1 for all x. Doesn't matter what x is. So we can rewrite this equation as 1 minus secant squared plus tangent squared. Right. Now, if also from trigonometry, we know that 1 plus tangent squared is equal to secant squared. So we can replace this 1 plus tangent squared, we can replace it by secant squared. So we get secant squared minus secant squared. Right. So is this equation true for all x on the interval negative pi over 2 to pi over 2? Yes, right, because secant squared equals secant squared, right? So it's true. Why did I not say it's true for all real numbers? Why is it not true that they're linearly dependent on negative infinity to infinity? Well, the functions secant and tangent are not even defined for all real numbers. Remember that secant is given by, okay, and tangent is given by, so actually let me do like a boundary line here. And tangent squared, okay, so I'm writing squared, but it's the same, just squared, is given by sine squared over cosine. Notice that both of these functions are not defined on any multiple of pi over 2, right? So pi over 2, negative pi over 2, um, pi, sorry, not pi. So not any multiple of pi over 2. What is it that it is? So they're not defined for pi over 2 plus 2k pi. Oh, okay. Okay, I remember now. They're not defined for any x value that looks like x equals pi over 2 plus a constant times pi, where this constant is an integer. So basically, this function, the domain of secant squared and tangent squared is all real numbers except pi over 2 plus integer multiples of pi. Like, in particular, pi over 2 and negative pi over 2 are integer multiples of pi over 2 plus pi. So I'm just taking an interval for which all of these functions are defined to begin with. Right? So it doesn't make sense to say that these functions are linearly dependent on negative infinity to infinity because they're not even defined on that interval. Okay? So you choose the largest interval for which they're defined. So actually, all of the intervals for which they're all defined have the same size. So I just chose negative pi over 2 to pi over 2. Because there's nothing else in this context that's making me choose one interval over the other, over another. Okay? So again, this is an example of a set of functions that are not linearly dependent, that are linearly dependent. So they are linearly dependent on the interval negative pi over 2 to pi over 2. Why? Because I gave you coefficients, not all 0. In fact, none of them are 0, but you only need one of them at least to not be 0, for which this equation, when you plug in the coefficients, is always true. And we verified it's always true for all x on this interval. Let's do another example. Are the functions, let's do sine x and cosine x, linearly dependent on some interval. So here I'm not even telling you on what interval to look for or what coefficients to look for. So if you're given a question like this, are the functions sine x and cosine x linearly dependent on some interval? Again, always the first thing you want to do is look at this equation here. So write a linear combination of the two functions you're working with. And for linear dependence, you're looking for an interval for which uh, not all of C1 and C2 are zero. So, okay, so I'm gonna write at least one of C1 or C2 is non-zero. And again, let me just call this equation star. So you're looking for an interval for which at least one of C1 or C2, potentially both, are not equal to zero, and star is true for all x in whatever interval you're saying you're working with or you're trying to find. So we're looking for at constants or coefficients C1 or C2, at least one of them non-zero, for which this equation is true for all x in some interval. Well, this is how you want to start all of these problems, okay, when you're looking for linear dependence. Now, you want to work with this equation. I'm going to rewrite it in a way that's going to be more enlightened. So I'm just going to subtract C2 cosine x from both sides. Okay. Now, are there constants not all zero for which this equation is true on some interval, for all x in some interval? Well, let's say that it were true. Let's say that these functions were actually linearly dependent. So what we're going to do here is this thing that is pretty nice. It's kind of called the proof by contradiction. You assume what you're trying to show, or the opposite of what you're trying to show. And if that leads to a contradiction, then whatever that thing was can't be true. So it's easier to see in practice. So suppose that they are in fact linearly dependent on some interval. So I'm gonna write linearly dependent as LD on some interval I. Well, by definition, that means that at least one of these constants is non-zero. Right? So let's say that without loss of generality, that C1 is non-zero. So assume C1 is not zero. Well, if C1 is not zero, we can divide C1 on both sides, and we get sine x equals negative C2 over C1 times cosine x. Now, is it possible for sine x to be equal to a constant times cosine x for any x for all x in some interval? It's definitely possible for specific x's, but not for a whole interval. Why do I know this? Well, you can look at the graphs. Remember that all that happens when you multiply by a constant is to either stretch or compress cosine, or you reflect about the the x-axis. So compare the graphs of sine and cosine. There's no way to compress or stretch cosine x vertically, or reflect about the x-axis for the graphs to match, for the functions to be equal. So in fact, this is impossible. So this equation, let's call it asterisk. So I'm going to write, but asterisk is impossible Again, it's possible for this to be true for specific points, specific x values, but not on a whole interval. But this is not possible, right, on any interval. So it is not possible for sine and cosine to be linearly dependent. And again, I can conclude this because if they were linearly dependent on some interval, it would lead to this equation, which we know is not possible. So it leads to a contradiction. So again, as I mentioned, when you're working just like this, it's kind of theoretical, right? You kind of have to justify why something like this is true or not. Let's do one more example. I'm just gonna do it in another video, just so it's this one is I think it's getting a little bit long, and then I'm gonna introduce a way for us to actually do this numerically with an exact algorithm. And you're gonna be thankful because you see how hard this is.